Hello, welcome to the History of Life and Evolution chapter. This is lecture video number 1. So, pretty much, this is our evolution chapter. The beginning of the chapter, we'll talk about history of life, how old the earth is, and things of that sort. Then we'll eventually get into evolution and the concepts of evolution. All right, so let's begin. Let's talk about Earth's history. So, Earth, it's pretty old. It's about 4.5, a little over 4.5 billion years old. How did we date it? How did we age it? I'll explain that to you in a slide or two. I'll let you know how we came up with that 4.5 billion number. So, the history of the Earth. What happened? So, at one point, the Earth was basically not really Earth yet. It was part of this giant mass of material. Okay. It was swirling around a mass of gas and dust. All right. That's what the Earth at one point was, part of this giant mass of dust. We weren't Earth quite yet. We weren't planets yet. The sun hadn't completely formed. All right. Over time, it started getting pulled together because of gravity, and you began forming what was the sun. The sun is generally at the center of a galaxy. Okay, at the center of a galaxy, you have the sun. The sun, and a lot of times they may be called stars. When you look up in the sky and you see stars, you're looking at other things that are like our sun. All right, so our sun is a star, in case you didn't know that. So what happened over time? Gravity started pulling it together. Okay, started pulling it together. Eventually, planets, debris started smashing into each other, and they started to form. And it kept happening, and it kept happening. And eventually, you had the sun. And our sun is not quite at the center of our galaxy, but it's off to the left. It's off to the side a little bit, and we go around the sun in an elliptical fashion. Okay, so not a perfect circle like this picture shows, but eventually the planets formed and they started moving around the sun due to gravity. So the gravity keeps us close together, keeps all the planets in our solar system together. All right. So our solar system, galaxies, they all formed in similar manner. So we are part of a solar system of 9 planets and the sun. Okay. So this is how it formed. So how do we know how old things are from the past? For example, I just told you the Earth is about 4.5 billion years old. Well, what do? We do what's called radiometric dating. We can use what's called a term called the half-life, and you're going to see that in a second. We're going to use certain things. We can tell how long a substance will last for or how quickly it breaks down. And based on how something breaks down, we can calculate the age of things from the past. All right. You've probably heard the term carbon dating, and we're going to talk about carbon dating in a minute. So let's first get some background so we can understand how these dating techniques are used. Some background information. Atomic number. Well, what is that? That's the atom's number. Well, the atomic number is always the number of protons. So here's, for example, carbon 12, carbon 13, and carbon 14. All right, pictures of them. Carbon 12 and carbon 13 and carbon 4, they all have the same atomic number. They all have 6 as their atomic number. What does atomic number mean? That means they have 6 protons. Carbon will always have 6 protons, no matter what. Its atomic number if the atomic number changes, the number of protons changes, you no longer have carbon. So if you have 5 or 7, you don't have carbon anymore. Okay, no longer carbon. You've changed the identity of the element if you've changed the number of protons, also known as the atomic number. There's these other things that elements or atoms have. They have neutrons, these N's, and they have E for electrons. All right. Usually the number of electrons is equal to the number of protons. Why? We will be talking about neutral atoms that do not have a charge. So for example, if it has 6 protons, it will have 6 electrons to balance it out and have an overall charge of 0. That will give it a neutral charge. So protons and electrons are the same. All right. Neutrons, though, those can be different. Since neutrons can be different, for example, this is a picture showing hydrogen 1, hydrogen 2, hydrogen 3. Hydrogen 1, no neutrons. Hydrogen 2, 1 neutron. Hydrogen 3, 2 neutrons. So isotopes are atoms of the same element. These are all hydrogen, but they have different numbers of neutrons. The neutrons can differ. Okay. What is the mass number? It is the total neutrons plus protons. So this one, hydrogen, tritium here has a mass number of 3. Why? 1 proton plus 2 neutrons, that equals 3. Deuterium, hydrogen 2, has 1 proton, 1 neutron. 1 plus 1 is 2. Protium, hydrogen that's called protium, just has a proton, no neutrons. So 1 is its mass number. So the mass number here is 1, the mass number is 2, the mass number is 3. Carbon 12, the mass is 12. Carbon 13, the mass is 13. Carbon 14, the mass is 14. Carbon 12, let's compare carbon 12 and carbon 14. They both have 6 protons. That's their atomic number. Carbon 12, what's 12 minus 6? 12 minus 6 is 6 neutrons. 14 minus 6 is 8 neutrons. Electrons are always the same as protons for these neutral atoms that we will be discussing. Okay? Now, some atoms, their nucleus is unstable, so it breaks down. And over time, they change their identity. All right? So they become something different. So, for example, carbon 14 over time breaks down and becomes nitrogen 14. Okay. Carbon, in case you're wondering, 6 protons, nitrogen has 5. So over time, when it breaks down, it's lost a proton eventually and it became nitrogen 14. So things break down into something else that is more stable over time. So why do we need to know about these? These are radioactive elements, which means they break down. Radioactive elements break down at a certain rate. When half of that element is left, we say that the amount of time that has passed is the half-life. So for example, carbon 14, which is radioactive carbon, carbon 12 is not radioactive, it doesn't break down, but carbon 14 does. Carbon 14 breaks down at a rate of 5,730 years for half of it to be broken down. So if you started out with 100 grams in 5,730 years, 100 will be divided into 50 grams. Another 5,730 years passed, 50 divided by 2 becomes 25. So this is the amount of time that's passed for half of it to be remaining. The way we've aged the Earth, they have found rocks on the Earth and aged them. They didn't use carbon dating because carbon dating is only useful to a certain amount of years. They used uranium dating, and uranium breaks down into lead, which is stable. Uranium is not stable. Uranium dating is how we figured out the Earth is about 4.5 billion years old. We've actually found meteorites that have crashed into the Earth, and we've dated those rocks to about a little over 4.5 billion years old. We've actually found rocks on Earth, I believe in Australia, that have dated to 4.3 to 4.4 billion years old. We've also dated rocks on the moon in the range of around 4.5 billion years old. So that is how we have dated that the Earth has been this long. So we've used radioactive isotopes. We've dated the Earth using uranium, which breaks down into lead. Living things don't have uranium in them. Living things, we do carbon dating, and we look at how carbon 14 breaks down for living tissue or living things. How does carbon dating work? Well, you start out with a known amount, and when you have half of it left, so 10 to 5, that means 5,730 years pass by for one half-life, number of half-lives. Another 5,730 years pass, 5 becomes 2.5. Another 5,730 pass, 2.5 becomes 1.25. I just keep dividing it by 2. Another 5,730 years passed, 1.25 becomes 0.625, and so on and so forth. You just keep dividing in half. All right, so we're looking at half-lives. And carbon 14 is unstable, carbon 12 is stable. All right, so how does carbon dating work? Well, it's kind of a weird concept. So you and me, we are alive. Living things need carbon. And we get it from our nutrition, from our food, from what we eat. So when we eat food, we take in radioactive carbon. No, it is not hurting us. It is not damaging us. It is part of our tissue. We have a certain percentage of our tissue currently that is carbon 14. We know it. It is a known amount. All right. Everybody who eats, who's alive, you are constantly taking in a certain ratio of carbon 14 compared to carbon 12, the stable versus unstable kind. The unstable one is carbon 14. So at age 0, we'll say that is when something dies. All right. When something dies, it is no longer taking in carbon-14. All right. So when something dies, carbon-14 doesn't enter anymore. So the carbon-14 that it is made out of will start to decay and break down at a rate of 5,730 years for half of it. Okay. So the ratio of carbon-14 to carbon-12, it's known. When it dies, carbon is not taken in anymore. You don't eat anymore. So if you or me die and we get buried and our body gets preserved somehow for thousands of years, since we stopped eating, the carbon-14 that we were made out of began to break down as soon as we died. All right? Then, over time, it breaks down at a rate of half of it every 5,730 years. So 50% of it is left after one half-life, 25% is left after two half-lives, 12.5% is left after three half-lives. You keep dividing in half and you get another half-life. And that's how you can tell how old something is. So if you found a piece of wood and it had 1, 2, 3 half-lives, it is 17,190 years old. Using this information, we're going to have to do some calculations. So let's see what works, what is expected of us. Here's sample question number 1. If you have 1/32 of your original sample of carbon-14 remaining, how many half-lives did you have? So you start with 100%. Okay, and here's the math on how to do it. After one half-life, half remains after the first half. So you start with 1, you divide it by 2, that's 1/2. That's the first half-life. Okay. Now we're not at 1/32, we're at 1/2 so far. Then you do it again. 1/2 divided by 2 again is 1/4. So 2 times 2 is 4. 1/4 remains after a second half-life. 4 times 2 is 8. So 1/8 remains after a 1/8 remains after a third half-life. 8 times 2 is 16. 1/16 remains after a fourth half-life. 16 times 2 is 32. 1/32 remains after the fifth half-life. So the answer would be 5 half-lives pass if you have 1/32 of the original sample left. Sample question number 2, and it's my tip to you, try to do them without seeing the answer first. So do them, hit pause on the video and try them. Sample question number 2, a sample of wood originally contained 88 milligrams of carbon-14. And it now contains 11 milligrams of carbon-14. Okay, so 88 milligrams of carbon-14 is now 11 milligrams of carbon-14. I gave you the half-life of carbon-14 is 5,730 years. All right, first question, how many half-lives did it undergo? And then the next question is, what is the age? So let's do it. Start with 88. One half-life gets you to 44. All right, 44 divided by 2 gets you to 22 after a second half-life. 22 divided by 2 gets me to 11 milligrams after a third half-life. So to get from 88 to 11, we halved it 3 times. 3 half-lives passed. That's the first answer. And if each half-life is 5,730, 3 times 5,730 gives you 17,190 years as the age of the wood. Sample question number 3. Gapionium, I made it up, has a half-life of 3 days. 3 days. If your original sample of gapionium weighed 20 kilograms, how much would remain after 12 days? All right, so let's show you how to do the math. So 12 divided by 3 tells us that it had 4 half-lives took place. Okay, so 12 days passed. Every 3 days was a half-life, so 4 half-lives passed. Okay, so we started with 20. 20 divided by 2 is 10 after one half-life. 10 divided by 2, 5 after a second half-life. 5 divided by 2 gives me 2.5 after a third half-life, but we need 4 half-lives, so 2.5 divided by 2, 1.25 remains after 4 half-lives. Okay, so the answer is 1.25 kilograms remains. All right, we will stop our lecture there.